In this video, I want to go over things you're responsible for in Module 3, and I am filming these review videos back to back, so it's going to seem like a lot of deja vu to me because we just got done talking about, or I just got done talking about Module 2 review, and we were talking about inferences for a single mean in Module 2. Here we're talking about proportions. Module 3 is all about proportions. And so we have the same, in fact, if you look at the slides, you're going to notice they look very, very similar. There was a lot of copying and pasting going on here. Now we're talking about a single proportion, comparing two proportions, comparing three or more proportions. And what you're responsible for are the pieces that we typically are responsible for. You need to be able to tell me, for instance, if we have a large sample or not. It's real important. It's always important, but it's real important with proportions because there's not a small sample technique to use here. I can't all of a sudden use a t-distribution for small samples, and so we need to make sure we have large samples, and the sample size criteria has changed. When we were dealing with means, it was very straightforward. We used the number 30 quite a bit. 30 or more was large, less than 30 was small. Now with proportions, it's different. It's n times p and n times q both have to be at least 15, and that's just weird. It's not simple. It's complicated. Now, what I will say about that is it's consistently complicated. So when we compare two proportions on the next slide, we have a couple of them, but it's the same thing. N times P and N times Q both have to be greater than or equal to 15. The assumptions are a little bit easier now when you're talking about a single mean. We need random samples. The approximate normal stuff doesn't work when you're working with proportions, so it never comes into play. It sometimes comes into play with means, but not proportions. So the only assumption we need here is there's a random sample taken from our population. So the assumptions are pretty straightforward. Only large samples, however. Confidence intervals, we'll let the computer do the math, just like we always do. I don't want you spending any time calculating confidence interval endpoints. However, I do want you giving me practical, theoretical, and being able to answer questions. When I say giving me practical and theoretical interpretations, we are 95% confident the proportion of all students who voted in the last election falls between 0.47 and 0.74, say. Just making up some numbers there. What do you mean when you say you're 95% confident? It's just a confidence interval, folks. In repeated sampling, 95% of the intervals created would contain the true population proportion. Okay, should have heard that before. We've seen that a couple different times. And then I'm going to ask you some questions. So if I have a confidence interval, and if I remember the numbers that I just said, let's say, for instance, it goes from 0.47 to 0.74, just to use that as a for instance, and I ask you, is the population proportion equal to 0.75? You're going to say, we are 95% confident the proportion is less than 0.75. If I ask you, is the proportion equal to 0.5? You're going to say at the 95% confidence level, might be 0.5, because 0.5 falls inside the interval, 0.75 falls outside. That's why we answer those questions differently. So I want you to approach the confidence interval for a single proportion exactly the same way you did the one for a single mean. Changing gears here considerably. We're going from quantitative data that gave us the means to the qualitative or categorical data that gives us proportions. Yet the way we look at these confidence intervals will be extremely consistent. Test the hypothesis. You guys tell me what the test is. Test to determine if the true proportion of students who voted in the last election exceeds 0.7. You come up with the null and the alternative. I'll give you a printout that gives you the test statistic and p-value. Or maybe in another context, you're generating it, and then you have to be able to interpret p-values. Go figure. Wish I had a nickel each time I say that this semester. You have to be able to interpret p-values. When p is low, you can reject the null hypothesis. And so you need to be able to do all of that in the context of the problem and in the words of the problem. On some of the stuff I assess you, or the projects, for instance, you're writing out your own answers, and I'm seeing if you're doing it correctly. In other situations like the quizzes, I'm giving you multiple choice types of question answers. You have to pick the right answer. But you need to be able to go through the 4 steps of the test hypothesis. That's working with a single proportion. Comparing two proportions, well, we just had n times p and n times q have to be greater than or equal to 15. Now I have a couple of them because I have 2 samples. I have n1 p1, n1 q1. They both have to be greater than or equal to 15. That means my first sample is large. Then I have n2 p2 and n2 q2. They both have to be greater than or equal to 15 as well. That means my second sample is large. We need both samples being large in order to use this technique. The assumptions, well, we have random. We need random samples and also independent. There is no paired proportion work. So we need random and independent samples. And then we do our thing, confidence intervals. Which proportion is bigger? Remember when we talked about means, we talked about the intervals. It wasn't necessarily the numbers. It was the signs attached to them. This interval here would give us a conclusion that said the first proportion is bigger than the second one. If the interval was entirely negative, the first one is less than the second one. And if we have a negative lower endpoint and a positive upper endpoint, that's where we can say at the 95% confidence level, we're not sure which proportion is bigger. The way that we interpret confidence intervals is exactly the way we did when we compared two means. And so our confidence interval interpretations really is answering that question. Which proportion is bigger? Sometimes we say we don't know. Sometimes we can say we do know, and we have this level of reliability to back it up. As far as the confidence interval calculations, nope, not you. You got better things to do with your time, so I'm not going to ask you to do that. We're going to let the computer do the math for us. We'll get the endpoints on printouts. In terms of the test of hypothesis, if you want to do a test hypothesis, you need to be able to specify the null and the alternative. I probably mentioned this in the Module 2 review, but when you're doing tests, you always need to be careful when you want to conduct a one-tailed test. If I say test to determine if this one exceeds that one, that doesn't necessarily mean it's a greater than test. Exceeds sure sounds greater than, but when we look at means, when we look at proportions, when we compare them, we look actually at the difference between them, P1 minus P2. If I ask you to show me that P1 exceeds P2, that is a greater than test. The alternative there would be P1 minus P2 is greater than 0. But if I ask you to show me that P2 is greater than or exceeds P1, that's a less than test. P1 minus P2 is less than 0. So just be careful on one-tailed tests whenever you're comparing two means or two proportions. Once you specify your null and alternative, the test statistic and the p-value are going to be found on the printout. Specifying the alternative is what drives the printout. It takes you to a specific menu within the software and you generate the printout. On the printout will be the test statistic and the p-value. And then you're going to state a conclusion. When p is low, you can reject that null hypothesis. There's sufficient evidence to indicate that the alternative is true. If p is high, you fail to reject, there's insufficient evidence to indicate that alternative hypothesis is true. We've looked at examples. Now you have to do the work. Practice, 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 practice. And that way you'll get good at it. And so that's comparing two means, which leaves us with just one more. Module 3 also looked at comparing 3 or more proportions. The assumptions. There is a sample size amount here. And there are some assumptions. We talked to them about them being called the multinomial assumptions. And so make sure you go back and take a look at the outcomes and independence and different pieces that we need for the assumptions. These are a little bit different than some we've seen before. Again, when we talk about comparing 3 or more proportions, we have our techniques, our confidence intervals, and our test hypothesis. However, as we saw with comparing 3 or more means, there's a specific order here. The null hypothesis is going to make some specific statements about those proportions. And the alternative is going to say, that's not true. And so we do a test to see if anything in that null hypothesis is wrong. At least 2 proportions are different than what they're specified to be. Okay, that's the alternative hypothesis. And you can actually state that a couple different ways depending on the scenario, but that works. So you're responsible for setting up the test. Again, that's on you. That test will drive how you generate the test statistic and p-value. I'll be giving those to you. And then you're going to make a conclusion. If your conclusion is that the null hypothesis is wrong, at least 2 proportions do differ from what they're specified to be, then you have some follow-up work. And this follow-up work involves confidence intervals. Here's your test. Here are your confidence intervals. And there's more than one. There's multiple confidence intervals. And depending on what we're doing, there's a couple different ways of doing this follow-up work. Now, I covered this when I went through the comparing 3 or more proportions lecture, the one-way study. There's a couple different, there's actually more flexibility with the proportions than with the means. In the means, we always specified that the means are equal to one another in the null. Here, there's a corresponding analysis where we specify that the proportions are all equal to one another, but that's not the only way that we can work these problems. And so based upon how the null hypothesis is set up, the follow-up work we do will differ. Let's assume that I will do the work for you. I'll do the math. You do the answers. And so you'll be able to interpret the results. There is a multiple confidence interval or multiple comparison type of idea, and our friend Bonferroni comes back into play. Rather than looking at a single confidence interval, we're going to look at multiple confidence intervals. And so we got to take care of our alpha, got to take care of our error. And we know how Bonferroni told us to work with that. So make sure you're comfortable looking at the output and being able to decipher the results. And so Module 3 involves proportions, very, very similar stuff. And the way I approached it, the way I taught it, the way I believe it is, it's very similar to working with means. There's some things that are different, like sample size requirements. Assumptions are different from time to time. But the general idea, our approach, is very, 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 very much the same. So hopefully I've presented it that way and it makes sense that way. But those are some good things to think about in terms of Module 3. If you have any questions, you always know how to get hold of me. Good luck.